Welcome back. So here we are at the end of the chapter. So last time we were talking about determining the pH when you were given strong acids and strong acids during a reaction. So on this case, we're gonna be talking about what happens when you have a weak acid. And we know that a weak acid can establish an equilibrium. So how do we do this problem? The problem is asking us to calculate the equilibrium constant, calculate the equilibrium constant for formic acid, which is going to be a weak acid because it's not one of the 7 strong acids. So we know that if we are going to calculate the Ka, we're going to put the concentration of the products over the concentration of the reactants at given powers. So that means we're going to have a balance equation. So let's begin with that. So we cannot do any of this unless we have a balance equation first. And we're looking for the constant for the acid. So that basically means the formic acid is going to be behaving like an acid when you put it in water. It's a weak acid, so it's going to be an equilibrium. So it's going to behave like an acid, so it's going to donate a proton. It's neutral, so it loses a proton, so it becomes negative. And the water accepted the proton, so the water is behaving like a base to give us the hydronium. So our K expression then is going to be Ka equals, and it's a balance equation, the concentration of hydronium times the concentration of formate or the conjugate base of formic acid over the formic acid. If we get those values, which are the concentrations at equilibrium, then we get our Ka. So what else do the problems tell us? The problem is telling us that the pH of this solution is going to be 2.38. And we learned earlier that pH equals minus log of the hydronium, and vice versa, the concentration of hydronium equals 10 to the minus pH. Remember that one? So since we know the pH, we can use this formula to calculate the hydronium, which basically goes right in there. So the pH will be the hydronium concentration at equilibrium. And since we know that the hydronium is 1:1 to the formate, or the conjugate base of the acid, then it also gives us the concentration of the formate. So what about the formic acid itself? Well, we know that the formic acid is 1:1 to the hydronium. So some of the formic acid became hydronium. So therefore, the concentration at equilibrium is going to be HCOOH minus the concentration of hydronium, because it's the same, is how much of the formic acid got consumed. And we know the value of this, so we can calculate the value of this. So let's see how we do that step by step. So we have our balance equation, like I just showed you. We have our Ka expression. We are using this formula to find the hydronium concentration, which is going to be 10 to the minus 238, which is going to be 4.2 10 to the minus 3 molar. And we said that it's 1:1 to this, so it's the same value as the formate, or the conjugate base of the formic acid. So we got these two values. So how are we gonna fill up the ice table so we can find the equilibrium concentration? That's what we need to find out to find the Ka value. Well, we're gonna do this. We're gonna set up the equilibrium expression. We know that initially we have 0.10 formic acid, 0 hydronium, 0 formate because the reaction has a start. We know that the pH concentration is gonna be that once we do hydronium concentration equals 10 to the minus pH, and the pH was 2.38. So when we do that, we get 4.2 10 to the minus 3, which is the same as we mentioned before as the formate. And we know that it's 1 to 1 to the acetic acid, so this much acetic acid is going to be consumed because it's 1 to 1. So we set up the expression. So this is how much you're going to have on equilibrium, the initial minus what became the hydronium. This is how much you have of hydronium on equilibrium, which is 1 to 1 to the formate. So when we plug these numbers, notice that we're taking 0.10 minus 0.0042. If we use the significant figure rules, basically we end up with the same thing. So we have to drop the rest. So the minus x is basically insignificant at this point. So we take those values, we fill up our equilibrium expression. So this will be how much formic acid we have on equilibrium. This will be how much hydronium and formate we have on equilibrium. We fill it up, and we come up with a equilibrium constant for acidity of 1.8 10 to the minus 4. Let's do something else. What about another term that we're gonna use? Is, you notice, this is the important part here. We took 0.10 and we took out 4.2 10 to the minus 3, or 0.0042. So when we do 0.10 minus 0.0042, we get 10 to the 10 minus 2 is 8. 9 minus 4 is 5. 9 minus 0 is 9. And 0 equals 0. So since this is a subtraction, 2 decimal places, 4 decimal places, our result can only be 2 decimal places. We drop the 5 and we have to round to 0.10. So that's what we end up with that, which means this value of x, it was too small. So it was insignificant, in other words. And so we end up with something like this. So how do we know? Could we have saved some time by saying, that x is going to be insignificant, I'm not even going to put it there? Well, we don't know until we do the problem. So how do we know that it's insignificant? Because we said, okay, so the hydronium concentration was 4.2 to the minus 3. The initial concentration was 0.10. When we take the ratio of the hydronium to the initial and we do the percentage, we get 4.2%. So that basically means from every 0.10 molar of the formic acid, only 4.2% of it became hydronium. In this case, 4.2 10 to the minus 3. So every time that the percent of ionization is less than 5%, it's okay to assume that the X is really small and to basically delete it. And we're going to see that really put into practice when we start with chapter 18. So remember for right now that how do you get the percent ionization? You get the molarity of hydronium divided by the initial molarity of the acid and multiply by 100. So let's do another one. So this one is determine the pH. On the other one, we were given the pH and we found the hydronium. This one is asking us to determine the pH. And they want us to evaluate if, considering that the X is really, really small, it's a valid assumption or not. And the advantage of considering the X really small is that it allows us to avoid using the quadratic expression. We can do the algebra really easy without having to do the quadratic expression. So let's see how we're going to do this. We're trying to determine the pH. We know that pH equals the minus log of the hydronium. So we basically have to find the hydronium. That's what we're trying to find. If we can find the hydronium, then we can tell you the pH. So we know that we're dealing with hydrofluoric acid. We're going to be using our equilibrium expression, so we better know the balance equation. So this always happens with water. Hydrofluoric acid is a weak acid, so it's going to establish an equilibrium. And it's going to behave like an acid, losing the proton. And the proton is going to go to the water, which is going to become hydronium. So Ka, which is 3.5 10 to the minus 4, is going to equal the concentration of fluoride times the concentration of hydronium over the concentration of hydrofluoric acid. If we do an ice table, where we're going to have the hydrofluoric acid, we do not include the water, it's a liquid, the fluoride, and the hydronium, we will know that initially we started with 0.250 molar of hydrofluoric acid. There was nothing of these two. We know that the hydrofluoric acid is going to go down by 1 or by x. And since everything is 1 to 1, this is going to go up by x, and this is going to go up by x, which means in equilibrium, you're going to have 0.250 molar minus x. You're going to have x and x. So when we put that into the expression, 3.5 10 to the minus 4 equals x times x over 0.250 minus x. At this point, we can say, well, I'm going to assume that the x is really small. So there's this x that is being subtracted. I'm going to basically don't even consider it. The other x on top, you have nothing to compare to, so you have to leave those two alone. So with that said, we're going to get 3.5 10 to the minus 4 equals x squared over 0.250, which means we're going to take the 0.250 and multiply by 3.5 10 to the minus 4. And that's going to give us x squared. So you're going to do that multiplication on your computer, and then we're going to find the square root, and that would be our x. So once we have our x, remember, x was the same as hydronium. Once you get your X, then you can do minus log of X equals pH. So that's how we do that, by knowing that the pH is going to need the hydronium and knowing that the hydronium is going to be one of the products. So a little bit better organized. So initially we have 0.250 of the hydrofluoric acid, 0 and 0 of that. Then we're going to take care of the change. It's going to go down by X, going to go up by X, and going to go up by X, which means the equilibrium expression is going to be like that, and like that, which will allow us to set up the expression like this. We are assuming that the X is super small, so we don't have to put it here, and we end up with something like that. We expand the operation and find our X. And our X is going to be our hydronium, which is going to give us our pH. So was this assumption valid, the fact that we just deleted the minus X? Well, let's see. X came out to be 9.4 10 to the minus 3. So that would be 9.4 10 to the minus 3 divided by the original concentration, and we came up with 4%. 4% is less than 5%. So yes, that was a valid assumption. Anything bigger than 5% tells you that it wasn't a valid assumption. And then you can do that, but basically following the same thing. The answer is down here, so make sure you can double check that you're doing it the right way. After you're done with that, you can do that one. The answer is down here. Make sure that you always show your work. And once you do that, then we can talk about something else. Polyprotic acid, which basically means there are acids that have many protons. For example, sulfuric acid have 2 protons that can be acidic. So polyprotic acid. And there are several examples of them. You got the every proton that is attached to that molecule is going to have a different equilibrium constant. So that would be the equilibrium constant for the first hydrogen. This would be the equilibrium constant for the second hydrogen. Notice how difficult it is for the second hydrogen to be ionized. So the possibility of ionizing is very, very small. And the reason is, after the molecule loses one hydrogen or a proton, then the nucleus can grab a hold of the remaining ones better. So it's going to be harder for them to leave. That's why the equilibrium constant changes so much, from -5 to -12. So that's the main thing about polyprotic acids, are formulas with more than one hydrogen that can be given away, or acidic hydrogens. And each hydrogen has its own K value. And then we can briefly talk about weak bases. So weak bases are going to be molecules like ammonia that like to take hydrogens or protons, but do not release any hydroxide. And they're usually going to have a lone pair, like for example, like ammonia, which is going to be like this, with a lone pair there. So this lone pair can grab into a H+, which needs 2 hydrogens, two electrons, and that's how that becomes a base. In addition to that, the anion of weak acids are going to be weak bases. So if I have HF, which is a weak acid, the anion, which is F negative, is also a weak base. So weak acids give you weak bases, weak conjugate bases. And then this is something interesting to know. You can relate Ka and Kb by doing this formula. If you multiply Ka by Kb, you get Kw, which at 25 degrees Celsius is 110 to the minus 14. So if you know one, then you can find the other one. And you can see it here. Hydrofluoric acid, this is the Ka, this is the Kb, which means that if you multiply this times this, you get 110 to the minus 14. And last but not least, it's going to be what we call a Lewis acid. So a Lewis acid is going to be a substance that can accept a lone pair. And with that, we come to the end of this section and the end of the chapter. So we know how to solve for hydronium or hydroxide, knowing that Kw equals their products. And we also know now how to find the pH or pOH of a solution. We know how to do it if we are dealing with a strong acid. And now we just learn how to do it by using the Ka if we're dealing with a weak acid. And with that, we come to the end of the chapter. So first thing we did, we dealt with the definitions. Arrhenius definition, basically an acid will increase the concentration of the proton or hydronium. A base will produce hydroxide. The Bronsted-Lowry is an acid donates a proton, the base accepts the proton. And we just saw the Lewis acid, which is the one that accepts a pair or lone pair electrons. And then we saw if we have an acid, whatever is produced is the conjugate base. If we have a base, whatever is produced is the conjugate acid. We saw the 7 strong acids, and any other acid is a weak acid, where you're going to then use the Ka. And that's what we're dealing here with weak acids or weak bases. And then we just saw how to solve for this. We study how adding a salt or dissolving a salt can affect the pH of the solution that is going to form. And we also saw that you can decide which one is more acidic or less acidic by studying the structure, such things as electronegativity, inductive effect, and all that we discussed before. And with that, that's the end of the chapter. So if you need to clarify anything, come see me at the office, come see me at the Science Learning Center, or study the tutorial videos posted on Canvas, listen to these recordings again, go to Alex and read the explanations, or go to your textbook and see a step-by-step example on how to do everything. So see you next time. Take care.